You haven't seen my face all semester probably because of our online class here. I'm growing my Christmas beard so I can look like Santa Claus for my granddaughter. And with that, let's launch into Moment of Inertia today. So why is moment of inertia important? It works in rotation like mass does for linear motion. Things go fast, accelerate fast, or slow depending upon moment of inertia. It can save energy. Why bicycle racers use thin light tires. But it can also save energy by storing energy. We'll talk about that in a second. You can find the moment of objects in a liquid. It's used in mechanical speed governors, and this is where the high moment of inertia regulates the speed. Engine flywheels store energy during part of the cycle so that the piston can get back to top dead center and fire again. If it doesn't get back, the engine's not going to run. The moment of inertia is important to keep elevators from going too fast. It controls the pitch of aircraft propellers, regulates the frequency of electrical generators. It was used in early cruise control and rocket inertial guidance, the gyroscopes. I recall an example of an air conditioning motor where they used heavy ferrite magnets on the outside of the rotor, so it was a high moment of inertia. It was a compact motor, but a high moment of inertia. What it did was it saved them a lot of money because they didn't have to use neodymium iron boron on an inside rotor. And for this air conditioning application, low cost was more important than high startup speed. You don't have to worry too much about startup speed on an air conditioner. Once you turn it on, you let it rip for a while, and then you turn it off. You don't turn air conditioners on and off real fast. So moment of inertia is an important consideration in a lot of different applications. What is moment of inertia? Let's consider this object underwater here, this guy right here. And we're looking at the force, dF, right here, which is the pressure times dA. And the distance from the x-axis is y. So we can say the moment, differential moment, is y times the force. Well, pressure is this constant gamma times y. So we can rewrite that differential like this. Gamma is just density times acceleration due to gravity. And we get y squared dA over here. So you can get the total moment equals density times acceleration of gravity times this integral. That is the moment of inertia, geometric moment of inertia. So the moment of inertia about the x-axis is this. Similarly for the y-axis. Now, the moment of inertia about this point right here, well, you can see that it would be the integral of r squared dA. That'd be the definition, by the way. It's defined that way. Well, that's just r squared is x squared plus y squared. So it's pretty easy to see that the moment of inertia about the central point is the sum of the two. The units, measurement units, length to the fourth, like meter to the fourth, millimeter to the fourth, or foot to the fourth. If you know the moment of inertia about the center of mass, you can find it anywhere else. Or if you know where the center of mass is and the moment of inertia somewhere else, you can find the moment about the center of mass. You can go back and forth. That's what the parallel axis theorem is all about. So once you know the moment of inertia at one point and the location of the other point, you can find it everywhere else. So we define the prime coordinates. That's this axis right here. And this is the centroid or the center of mass. So Ix about the origin here is just going to be the integral dy plus y prime squared dA. And you can break it down using a little bit of algebra. I'm not going to go through all that algebra. The important thing I'm going to talk about is right here. This is finding the center of mass. But in the prime coordinate system, the center of mass is at 0. So this integral becomes 0. And we get simple expressions for the parallel axis theorem, for the x-axis, for the y-axis, for the z-axis. Radius of gyration. It's the distance. If all the mass were concentrated at this radius, it would have the same moment of inertia. And it's simply the square root of moment of inertia divided by the area, total area. This just illustrates how to integrate. You can integrate two different ways for area. You can also do it radially, polar. You guys have seen that before. You should have learned this in your calculus classes. Okay, so let's find out the moment of inertia of this guy right here. We want to find it about the center of mass, the centroid, and about this axis right here, and then the polar center moment of inertia. And again, this is through the centroid, part C. And we can get it about the center of mass by just getting the integral from here, minus h over 2 to positive h over 2. And then y squared, y prime squared, I should say, y prime squared, dA. Well, that's the total width, B, times dy prime. So we get this expression that's h over 2 cubed times b, and it's twice because we got the upper limit subtract the lower limit. So 1/3 h over 2 cubed times 2. 1/12 bh cubed is the final result when you get that. Now, let's find it about this axis, the next axis. And for that, we have to add the h over 2 squared that's the distance in the y direction squared, and times the area, which would be BH. So this is, of course, 1/12 BH cubed. This is 1/4. When you square the 2, becomes a 4. 1/4 BH cubed. So the result should be 1/3 H cubed. And that's exactly what we get here. Okay. And then about the center of mass, well, if we go back a bit, we would see that the y prime is a very similar expression, but instead of BH cubed, it's HB cubed. Because you're rotating it, it's H and B are swapped when you're finding the moment of inertia about the y prime axis. So you just add the two together and you get this expression.